The entire web, literally everything you do online, runs on a secret language. It's this constant, lightning-fast conversation happening behind the scenes. And today, we're going to learn how to speak it. We're talking about HTTP.
You know that moment, right? You see a link, you click it, and bam, a new page just appears. But what actually happens in that tiny sliver of time? Well, it isn't magic, it's a conversation. A very fast, very structured conversation that makes the whole internet work.
So, before any pictures or text can show up on your screen, the two sides need to agree on how to talk to each other. Think of it like a universal handshake, the basic ground rules for every single conversation on the web.
And at the absolute heart of it all is HTTP. It's the web's lingua franca, its common language. It's just a clear set of rules that your browser and a website server both agree to follow. It doesn't matter if your laptop is in Tokyo and the server is in Toronto, they can understand each other perfectly because of HTTP.
Now, in every one of these HTTP conversations, you've got two main players. First, there's the client. That's your web browser, your phone, whatever it is that's asking for information. And on the other side, you've got the server, which is where the website lives and answers those requests. And here's the key. The client always has to speak first.
What's really wild about this protocol is a core idea called statelessness. Basically, it means HTTP has a terrible memory, on purpose. After a server sends you a web page, it completely forgets who you are. Every single click you make is a brand new, unrelated event to the server. This sounds weird, but it's actually what allows the web to scale to billions of users, because it means any server in a giant data center can handle your very next request without needing to know your history.
Okay, so the client always starts the conversation, but what does it actually say? Let's pop the hood and take a look at the anatomy of that first message your browser sends out. So a raw HTTP request might look a little intimidating, like a bunch of code, but it's really just a simple structured text message. It's got three main parts: the method, which is the action you want to take, the URL, which is what you want to take action on, and the headers, which are just extra instructions.
Let's start with the method. The easiest way to think about it is as the verb of the request. It's one simple word that tells the server exactly what your intent is. You're not just pointing to a web page, you're telling the server what you want to do with it.
And the most common verbs are super straightforward. A GET request just says, hey, can I fetch some data? Like loading a web page. Post is for creating something new, like when you submit a contact form. Put or patch is for updating something that's already there. And delete, well, you can probably guess what that one does. This simple vocabulary keeps the entire web organized. Now, for the headers. This analogy is just perfect. Think of the headers like the address, the return address, and all the handling instructions on the outside of a parcel. The actual contents, maybe a photo or some text, that's called the body. The systems handling the message, like the Postal Service, they don't need to open the box. They just read the outside to know where it's going and what to do with it.
All right, so the server gets the message. It reads the instructions, it processes the request. Now it has to send a reply. So let's flip the script and look at the other side of this conversation. The server's response.
And hey, look at that. The server's response looks pretty similar, right? It's got its own set of headers, and it has a body that usually contains the data you ask for. But that very first line contains the single most important piece of info in the whole exchange, the status code. A status code is just a 3-digit number, but it's a universal signal that tells you the results of your request. It's the server's super quick way of saying, yep, got it, here you go. Or, you might have made a typo. Or even, oops, something broke on my end.
And these codes are all neatly organized. Anything starting with a 2, like 200, means success. A 300 level code is for redirection, like when a web page moves to a new address. Codes in the 400s mean the client, that's you, messed up. And if you see a 500 level code, that means something went wrong on the server side.
And of course, we have to mention the most famous status code in the world, 404 not found. It's the classic client error, simply meaning you asked for something that just isn't there. We've all seen that one a million times. So that's the basic back and forth. But HTTP handles way more complex conversations behind the scenes, all to keep the web secure and running smoothly. Let's look at a couple of those advanced chats.
For security reasons, your browser won't let a script from one website just grab your data from another, right? But sometimes that's necessary. So the browser does this polite little dance first. It sends what's called a pre-flight request, which is basically it asking, hey, yourbank.com, Is it cool if this other website sends you some data? The server then replies with a, yeah, sure, and lists the rules. Only after it gets that permission slip does the browser send the real request. It's a quick, automated permission check that happens all the time.
HTTP is also brilliant at being efficient, mainly because of something called caching. The first time you ask for, say, a logo image, the server sends it to you. But it also includes a little tag, kind of like a version number, called an e-tag.
Now, the next time your browser needs that logo, it says, hey, server, I need the logo again. And by the way, the version I have is this e-tag. The server looks, sees that the logo hasn't changed, and replies with a tiny little message, a 304 not modified status code, and that's it. It doesn't resend the entire image. Your browser just uses the copy it already has. This saves a mind-boggling amount of data and makes the web feel so much faster.
You know, HTTP has been around since the very beginning of the web, but it's not some dusty old protocol sitting on a shelf. It has been constantly evolving to keep up with the insane demands of the modern internet.
The very first versions were super inefficient, opening and closing a connection for every single file. Then HTTP/1.1 came along and allowed connections to stay open, which was a huge leap. After that, HTTP/2 introduced multiplexing, which let us download tons of files all at once over a single connection. And now we have HTTP/3, which is built on a totally new foundation called Quick that makes our connections faster and way more reliable, especially on shaky network.
When you step back, HTTP is this beautiful example of a simple idea that evolved to handle incredible complexity. It's the invisible, unspoken language that connects our entire digital world. And with data moving faster every single day, it really makes you wonder, what's the next handshake the web is going to need to learn?
So, you think a firewall is enough to keep your organization safe? Well, you might want to stick around. We're about to dive into something called Zero Trust, and it's a pretty radical shift in cybersecurity that basically assumes your defenses have already been breached. We're going to break down what it is, why it's so crucial in our cloud-first world, and how it completely changes the game.
Let's just start with a dose of reality, okay? Look at this number. By late 2022, the average organization was getting hit with over 1,130 cyber attacks. Not a month, not a year, every single week. That is an absolute tidal wave of threats. And it proves one thing for sure. The old walls we used to build just aren't holding up anymore.
For years, we all used this castle and moat model for security. You know, build a really tough outer wall, and once you're inside, you're trusted, you're safe. But that just doesn't work now. With people working from everywhere and apps living in the cloud, the inside of the network is, well, it's everywhere. And that's where Zero Trust comes in. It flips that whole idea on its head and says, nope, we don't trust anyone by default. You have to prove who you are every single time.
So, why exactly is that old castle model failing so badly? The short answer is that the world it was designed to protect just doesn't exist anymore. The whole idea of a perimeter has basically vanished into thin air.
I mean, just look at the complexity we're dealing with today. Our applications aren't these big single things anymore. They're made up of tiny little pieces called microservices that are scattered across different clouds, and they can pop into existence and disappear in the blink of an eye. You've got users and their devices connecting from home, from coffee shops, from all over the world. You see the problem, right? There's no single border left to defend.
Okay, so if the old way is broken, what's the fix? Well, this is where the Zero Trust philosophy comes into play. And it's so important to get this. This is not some piece of software you just install and forget about. It is a fundamental shift in how you think about security. This one simple phrase is the absolute heart of the entire philosophy. Never trust, always verify. So what does that actually mean? It means it doesn't matter where you are on the network. Inside, outside, irrelevant. You get 0 free passes. Every single request to access anything has to be checked out with the same level of suspicion.
Okay, so principle number 1 is to verify explicitly. This is not your typical one-time login. It's a constant, ongoing process. Every time you try to access something, the system is asking, who is this user? Is their device healthy and secure? Are they connecting from a weird location? Trust isn't just given. It has to be earned over and over again, from moment to moment. Principle 2 is all about least privilege. The best way to think about this is like a key card at a hotel. It only opens your room and maybe the gym. It doesn't open every single room in the building. We do the same thing with access. We give users the absolute minimum they need to do their job and nothing more. That way, if an account ever gets compromised, the attacker is stuck in a tiny little box with almost nowhere to go.
Now, this last principle is a bit of a downer, but it's maybe the most critical one. Assume breach. We basically operate as if the bad guys are already inside our network, and this mindset forces us to build defenses that limit how far they can move. We do this by chopping up the network into tiny segments, encrypting everything, and constantly using analytics to spot anything that looks even slightly suspicious.
The philosophy totally makes sense, right? But how in the world do you actually build it? Let's take a look at some of the key technologies that make Zero Trust a practical reality. A really foundational technique here is called microsegmentation. Think of it like this. The old castle and moat model was like a city with one giant wall around it. Once you got inside, you could run around anywhere you wanted. Microsegmentation is more like a modern city, where every single building has its own security desk and its own keycard access. So even if you manage to get into one building, you can't get into the next one without getting verified all over again. It's all about containment.
Hey, remember all those little microservices we talked about? Trying to secure how they all talk to each other can be a total nightmare. And that's where something called a service mesh comes in. Just think of it as a really smart, dedicated traffic cop that sits in between all of your services. It manages all their chats, enforces security rules, and the best part is developers don't have to change a single line of their code.
A service mesh basically has two parts. As you can see here, you've got the control plane. That's the brains of the whole operation. It's where you set all the rules. And then you've got the data plane. This is like a network of tiny little bodyguards, or sidecar proxies, that you attach to every single microservice. The brains tell the bodyguards the rules, and the bodyguards enforce them right there on the ground, checking all the traffic.
So the whole process is actually pretty elegant and simple. First, an admin sets a policy in the control plane, like Service A is not allowed to talk to Service B. Then the control plane beams that rule out to all the little bodyguards. When Service A tries to connect to Service B, its bodyguard steps in, looks at the rule, and just stops the connection cold. And all of this happens completely separate from the actual application. It's pretty cool.
Okay, so we've talked about the philosophy and the technology. So what does this stuff actually look like in the real world? Let's put all the pieces together.
You know, when you boil it all down, Zero Trust is really about asking and answering some key questions for every single request. Who or what is making this request? Are they allowed to talk to this thing? And under what exact conditions? It's all about applying these super specific identity-aware policies to absolutely everything.
And here you go. This is a perfect example of what that looks like. This is a policy screen from a tool like Microsoft Intune. Now, you don't need to know the specific tool, just look at the level of detail you can get into. An admin can set rules for everything from how long a pin has to be to requiring a specific kind of hardware chip on a device. This is exactly what we mean by granular control. These are the nuts and bolts of Zero Trust. Now, for services to be able to talk to each other securely, we need something called mutual TLS, or MTLS. So think about it like this. When you visit your bank's website, your browser checks the bank's ID to make sure it's legit. That's normal TLS. With MTLS, your browser checks the bank's ID, and then the bank also checks your browser's ID. It's a two-way verification that makes sure both parties are exactly who they say they are before any data gets sent. And here's the payoff. The proof is in the pudding, right? This table shows a super simple test. A policy was created to block one service from talking to another. And when the attempt was made, what was the result? A big, fat 403 forbidden error. The connection was stopped dead in its tracks. The policy worked exactly like it was supposed to.
So what does all this mean for the future? Let's zoom out a bit and look at why this shift isn't just a good idea, it's pretty much inevitable for modern security.
The benefits of doing this are just massive. You get incredible control by slicing up your network and authenticating everything. But the biggest win, the real game changer, you absolutely crush an attacker's ability to move around. A single breach doesn't mean they own your whole network anymore. Instead, they're trapped, contained, and that gives you a fighting chance to find them and kick them out.
And honestly, it's only going to get smarter from here. The next wave of Zero Trust is going to be powered by AI and machine learning. Just imagine systems that can automatically figure out what normal behavior looks like, predict where the next attack might come from, and respond to threats in real time, all without a human having to lift a finger. That's the future we're building towards.
So, we'll just leave you with this final thought to chew on. The perimeter is gone, the castle walls have completely crumbled. So the question you really need to be asking yourself is this: what are you still trusting without question? Because in this new age of security, the only right answer should be nothing.